let's get started with review. All right, the first thing I gave you to do, the first lesson was Hubble's law, and it wasn't all of this stuff has all been async. So I want to kind of go over it with you and make sure you understand. Now, the thing about Hubble, Edwin Hubble, almost 100 years ago, is that he made two massive, great discoveries. Each one alone would have made him one of the greatest astronomers ever, but he made two of them. All right, we know the first one was that there are galaxies outside the Milky Way. The Milky Way is not the entire universe. It's hard to believe that not even 100 years ago, we thought the Milky Way was the entire universe, that the universe was only about 100,000 light years across only. That's so far. It's just so crazy. But we found out that it's hundreds of billions of light years across now, because all of the galaxies that are out there. But then he made another discovery, and he found out that those galaxies are all moving away from us. We're going to collide with Andromeda. Andromeda is not moving away from us, but that's because we're under the local influence, each other's gravitational influence. Okay, as a group, we've got a group of galaxies around us. As a group, we're moving away from every other galaxy out there. And they're moving away from us. And the farther away they are from us, and this is what that really bad assignment I gave you to do that didn't work. As we're farther out you go, the farther out a galaxy is from us, the faster it is moving away from us. Okay, and that tells us that the universe is expanding. We'll discover some really weird things about that here in future lessons. There's some really weird things going on out there. I say weird because we've just discovered them, and we think our brains have a hard time comprehending what's going on with that. So that was Hubble's law. Hubble's law basically it's an equation that tells us how fast the universe is expanding. That's basically what it's all about. And we're not going to go into that equation. There's a Hubble's constant in it, which has been argued. They don't know what that constant really is. Right now, they're guessing it as one thing, but in the past, it's been another thing. And so they're trying to figure out how to measure this and get the actual constant. And then we'll know exactly how much the universe is expanding and some other things as well. All right, so that is Hubble's law. All right, the universe is there's other galaxies out there outside the Milky Way, and they are all expanding away from us. So the universe is expanding. Now, I'll give you a little heads up here for something we'll talk about in the future. If the universe is expanding, what is it expanding into? That's just something to think about. We'll talk about that later. Okay, then I talked about if Hubble's law, I didn't talk about this, it was in the video that we watched. If Hubble says that the universe is expanding, it has to be expanding from something. Yeah, I just asked you what's expanding into, but it also had to be expanding from something. And that's where the Big Bang came into being. All of these galaxies, all the matter, energy, forces, everything in the universe used to be, as we've calculated, one little spot, okay? It's just an infinite amount of energy, basically, in an infinitely small spot. That's just the ultimate black hole kind of thing. And then for some reason, nobody knows, boom, it exploded. Now, it didn't make a sound. There was no sound at that time. There were no forces. There was no matter. It was all just energy. And that whole entire video, let me bring this up here. There it is. Oh, yeah. No, I got it here. Let me bring this up because I want to kind of discuss this a little bit with you, because I'm going to answer a question that I've been putting off for I got the wrong thing. That I've been putting off for the entire year. I'm going to answer it today. All right, now you remember you watched the video and I had you order all of these in the order that they happened in the Big Bang. It's hard to see, it's kind of small. I can't see it too well, so I'm going to turn off my camera to make it bigger for me. All right. There is the sequence of events that they have calculated with math to have happened right after the Big Bang. And when we're talking about right after the Big Bang, we're talking most of this stuff happened before the first second was completed. And so the first second, we had all this kind of stuff. The energy expanded. It cooled off enough that we started forming matter, but the matter was so hot and energetic, it would become energy again. But eventually, electrons were formed. And before that happened, the four forces came out. There was matter and antimatter that would annihilate each other. And fortunately, for us, for every 1 million antimatters that were formed, 1,000,001 matters were formed. And so after all the annihilations, all that was left was matter, which is what we have, which is good because that's what we are, right? So that was a good thing. So they've calculated all of this. This is all due to math models. Obviously, nobody ever saw this happen. We have and this is interesting. The whole point of particle accelerators, smashing atoms together, is to try to recreate the Big Bang and see what happened after the Big Bang, how that all works. And right now, we're just finding out all the particles and things that are involved that happen and when they happen and how they happen. And so all of that happened prior to basically the first second. The rest of this, there's about, then it goes into the rest of the time. But it's just, I think there was a soup of electrons 380,000 years, after 380,000 years. So there's the beginning of after the first second, I think, right there in that sentence. So a lot happened. All right. Obviously, nobody saw it, but we're trying to recreate it in the lab, so to speak, using particle accelerators. Okay. So here I'm going to answer the question. The question that I've been asked almost every year by students is, do I think there's other intelligent life out there? And I have the unequivocal right answer to this. The answer is yes, or it could be no. All right, that sounds wishy-washy.
It kind of does, actually.
Huh? Yeah, we're intelligent. Yeah. Well, yes, we are. We may be dumb, but we're intelligent. All right. We may do dumb things, but technically we're considered intelligent. All right. So here's why I'm giving this wishy-washy answer. Okay. So if you look at everything that had to happen just right, we had to have gravity come out of this Big Bang with just the right size. If it was too big, everything would have fallen back together and the universe would have never formed. If it was too small, everything would be everything would have flown apart before matter could have formed, right? So gravity had to be just right. The other forces had to be just right for this to happen. It had to happen in just the way it did. If gravity hadn't formed first as a force, nothing would have stuck together for the other forces to take effect. There is, let's see, if we hadn't produced more matter than antimatter, there wouldn't have been any matter in the universe. It would just continuously been energy, and that's all there would have been. That's just some of the things I can think of from this. So all of that had to happen just right. Now, other things, as you know, have to happen just right. You have to have a star that's not too big and radioactive, right? Putting out so much radiation, it just fries everything. Planets have to be the right size. They have to be the right distance from their star for life to be able to survive. Not too much rid of. There has to be, the planet has to protect them, right? Magnetic fields, atmospheres, that kind of thing. And then even if you have that, doesn't mean that life is going to form. Certain things have to happen for life to form. And then for life to continue to evolve on the way to being intelligent. I mean, we've had, 5 major extinction events that we have come back from. What are the odds that we would have life come back after one single massive extinction event? And yet we've had 5 of them and we still have life going on. There's just so much out there that is against life being able to form and thrive on a planet. So my answer is, you look out there, the billions of galaxies with billions of stars in them and trillions of planets. There's got to be other intelligent life out there. However, given all the odds, the right forces coming out, the matter to antimatter ratio, the Goldilocks planets, all of that stuff aligning just right. Maybe it takes all of that for the one chance to have intelligent life evolve and thrive. So that's my answer. It's either, yeah, obviously there's so much out there that's got to be, but maybe there's so much out there because that's how many out of all of those, only one has the exactly right circumstance through all of that to form intelligent life. So there's my answer. It's highly unsatisfying, but I think it's highly accurate as far as what we know. Everything goes. Okay. Let's get back to just our blank here. Okay, so then Big Bang. Now going from the Big Bang, there's lots of things that came out of the Big Bang. And if you type in comments, keep going. I'm going on, but we'll keep going. Yeah, it'll be depressing, but maybe if that extinct civilization had continued to thrive, they would have come and killed us off. You never know. Say what?
It'd be like looking at a zoo.
It would be like looking at a zoo. Yeah. Everybody go look at Earth. Yeah. Look at all that quote unquote intelligent life down there killing itself. Okay. All right. So lots and lots of matter. Now this is interesting. You know, we've all studied chemistry and the periodic table and all of the atoms, and then there's subatomic particles, quarks, and things like that. Just crazy amounts of matter out there. The matter that we interact with, that we can see, you know, the stars, the planets, air, us, all of that stuff, that only makes up 5% of the universe from what we've calculated. And we call that normal matter. But if it's only 5%, I think we're more abnormal than normal. But, you know, we're intelligent. We discovered this. We make the rules. So that's 5% is normal matter. 5% is normal matter. 27% is dark matter. We're going to learn what this stuff is. So I'm not going to go into great details. But dark matter is actual physical matter that we don't interact with. You've got it going through you right now. You know, regular normal matter holds together because it interacts with itself. You're not flying apart or anything because your matter in you likes to stick together. Okay. Normal dark matter doesn't like us. That's why we can't see it. We can't interact with it. We can't feel it. Nothing like that. It just, we don't know each other exists, basically. And then 68%, the rest of the universe is something called dark energy. They call it dark energy because they have no idea what it is. They have no idea. They'll tell you that. We have no idea what it is. So we call it dark energy. They don't know what dark matter really is, so they call it dark matter. And it's also called dark matter because we can't see it. But dark energy we can't see, but we can see the effects. If it wasn't for dark energy, the universe would not be expanding. I will tell you this, and we'll talk about this at another time in more detail, but I'm going to leave you with this. The reason why the universe is expanding is because space, which we'll find out is not nothing, it's actually something. Space itself is being created from nothing. We have new space being created from nothing, and it's expanding the universe. That's you make it's growing. So new cells get made when you grow, right? Now, of course, we know new cells split off of old ones, but that's not really what's happening here. New space is being created from nothing. That seems like it's impossible, but this is well beyond my training. But theoretical physicists, particle physicists have proven that this is possible mathematically, and we're seeing it happen because the universe is expanding. The galaxies aren't getting bigger. The stars aren't getting bigger. They're just moving farther apart, meaning the universe is getting bigger. And again, I will let you ponder the question, if the universe is expanding, what's it expanding into? Okay, I have a video I want to show. Usually I love, Lily, that is such a good question, and we will discuss that, but I'll answer it really quickly for you. Because the first time we ever really realized it is because galaxies don't rotate the way they're supposed to. If you remember, the farther away a planet is from a star, the slower it orbits. Yeah. The same thing, it doesn't matter what it is. Stars in a galaxy, the farther away they are from the center of the galaxy, the slower they should orbit. It turns out that at a certain point, all the stars, that they follow that rule for part of the galaxy going out from the center of it. But then the farther out you go, all the stars orbit at exactly the same velocity. And why is that? Well, there's some kind of gravitational influence that we can't see. And that was, dark energy. Then they found some other things. They found light being, what's the lensing? Remember how we find exoplanets is because light gets lensed around the planet? They find light getting lensed around blank areas of space. I'm like, whoa. Well, there's not a planet there. It's too big for that. We don't know what this must be dark matter. So there's plenty of evidence out there for it. Although I will caveat that and say that there are scientists that think there could be other explanations at this point. We haven't proven that there's dark energy, but right now it's the best model that we have, and we're still trying to find out if it's actually that's what it is. So being a high school class, me being a high school teacher, we're going to go as if it's fact because that's the best we know right now. But keep in mind, it could change. We could find out tomorrow that they made a discovery that, it's not dark energy. It's a new force that we've discovered or something. You never know. All right. Okay. Let me put on this video. Just give me a second here. This is a very short video. It's about 5-6 minutes, a little over 5 minutes long. It's a cartoon. It looks kind of cartoonish, but to tell you the truth, this is a very deep concept, and it's something I'm showing you seriously. Okay, it's not a joke. So watch it carefully. I will say that what this is the first evidence that they came up with for quantum mechanics. and we're not going to really discuss quantum mechanics on that. This is just strange, and we're having trouble getting it loaded up. Ew. I may have to. You seeing it?
Yeah.
Well, it's not planting on mine. Okay. This is the first evidence we had of really weird behavior, and I'll try to explain it a little bit after he's done with his little thing. There we go. All right, I just thought of something. I want to see if we can do this. All right, you can actually imitate this with your fingers. You can actually see this interference of light waves by using your finger. If you take your thumb and index finger, and you know how you ever do that, squish somebody's head with your finger. Well, look at a light. Look at a light through your fingers. Put them close together. Move them slowly together. You'll start seeing dark lines form. Okay. And if you move your fingers just a little bit, those lines get bigger and bigger, but they don't move. They stay in the same place. That's where light is actually acting like it's going through a double slit. And the light waves are canceling each other out, and you're seeing nothing. Those lines are interference patterns as light acts like it's going through a double slit. So, do you see it? Yeah. Pretty cool, isn't it? Yeah. Yeah. It's a cool little experiment. Howdy. Okay, so that was the double slit experiment. It's been done many, many, many times, and it's done this every time. So what basically that is saying is that electrons do not exist as particles until you look at them. All right, they exist as waves. And not as waves of energy or anything like that. They exist as a wave of probabilities. There's a probability that this electron exists over there, or no, it exists over here, or there's a probability it exists somewhere else, and it exists in all of those places until you look at it, and then it exists where you're looking at it. It's now. Do I really understand that process? Does anybody? No. Nobody knows what that is, how that's working, and what causes that or anything. But that is part of the strangeness of the quantum world, of the tiny, tiny little world of subatomic particles. And we're going to do a lot more looking at that. Now, in the future, in our next classes, I'm going to be showing you these videos that have to do, and mostly they're from this particle physicist called Brian Greene. He's very famous on PBS and for writing some books on this and for string theory and things like that. We're going to be watching his videos, and trust me, they're very entertaining. They're very well done. You will like them. For the graphics, you will be completely confused by the information that he's telling you. So if you're going to be confused, why am I showing it to you? Because this is the current understanding of the science. And take out of it what you will. Just remember that as much as you don't understand what they're talking about, they don't understand it either. They don't understand why this works. This is just observation backed up by mathematical models. This quantum behavior that we're talking about is well documented and well observed in experimentation. So this is the way that subatomic particles react and they act. And then we'll be talking about what this has to do with cosmology as we go along and the weirdness of it. Okay, so if you have any questions on it, let me know. I'll be glad to try to answer them for you as best I can right now. But this is as far as the lecture I wanted to go. This was all I was going to do with it. So you are free to go. No reason to stick around if you're all done. And that's all we're going to cover today. So if you leave, have a great day. If you've got some questions you want to hang out and ask them, feel free to do so.